Good morning. Hello. Your midterm scores have been graded. They've been released. Was the score that you got kind of what you were expecting? Was it higher than you expected? Lower than you expected? About the same? Reasonable? Yeah. Okay. I will say this is the highest that anyone has ever scored on any one of the exams that I've written. So thank you all for your hard work. I think this was actually a harder exam than in summer when I taught this, and the average in summer was like 6% less than the average this time. So yeah, good job. However, there are still a lot of confusions that I saw. So I wanted to spend a little bit going over some midterm questions because I thought that would probably be helpful, just to kind of recenter all of us, bring us back. Although maybe it would be better to have it towards the end because I assume that a lot of people are late, and I'm assuming that maybe the people who are late are also the people who missed some things. But I'll still go over it now. They can watch back. So yeah, for the most part, everything went very well. This question was supposed to basically test your understanding of when CMOS draws power. And about maybe, 3/5 of the class got this first point right. This is kind of the entire thesis. This first sentence right here, this is the entire thesis of this entire paragraph. What determines when CMOS draws power? Shout it out. When does CMOS draw power?
Switching.
When switching, yeah, right. It's not necessarily connected to 0 volts, 1 volt. Of course, like it needs to be connected to some sort of power source, but the main thing is CMOS only draws power when switching. And if you learn anything about CMOS from this class, this is basically the only important thing. Is that CMOS draws power when switching, and that's when it only draws power. That's the entire reason why we're able to fit like 1,000 million transistors on a single chip. It's because almost none of them are drawing any power. If they were all drawing power when connected to 1 volt, then your chip would burn up and it wouldn't work at all. The entire purpose of CMOS is that it only has little power spikes right at the clock. When the clock goes, then all of the wires will all shift at once. They'll all charge up, and then power draw ends. And then there's another clock edge. Then boom, there's a spike, and then power draw ends. And then kind of the purpose of a lot of CAD tools nowadays, computer-aided design tools, it will be to try to make the spikes, the big old spikes, they will try to even them out so that maybe instead of a spike, if we imagine that this would be current, and let's say maybe this is the clock edge, instead of a big spike, maybe like this, maybe this would be at, 70 amps, right? A lot. Can totally happen. You can have incredible power spikes if you're at 1 volt, right? If you have a 70 amp spike and your operating voltage is 1 volt, then what is the wattage at this point? So it's 70 watts. Yeah, so you can have a spike that's 70 watts. I'm sure you've seen NVIDIA graphics cards. They can spike way higher than this. They could spike to maybe 200 watts. So 70 amps. A 70 amp spike is totally reasonable. So the idea is that, well, maybe VLSI engineers can come along and then they can add capacitors and things to make it so that when a spike happens, maybe it more looks like this. So it's spread out and maybe only goes up to 30 amps. Okay, anyways, cool. So I won't spend any more time on this, but okay. Now this question, I think was the lowest scored question, one of the lowest scored questions. I think only about half of people got one of these right. So I don't remember which one exactly. But okay, so let's go through it. Clock to Q delay. Okay, what is the clock to Q delay here? Yeah, so it is 1, 2, 3. So clock to Q is 3 nanoseconds. Good. Okay. I think like 95% of people got this correct. And then immediately after that, then it dropped to like 50%. Okay, okay, let's do question B now. Question B was okay still. So assume 2 nanosecond setup time. So if we draw out the timing aperture, so it would be, so before the clock edge, 2 nanoseconds, and then it says 1 nanosecond hold time. So the timing aperture would end here. So now we have that this region right here, this is when D needs to be stable between. So it asks, is there a setup time violation, hold time violation, or no violation? So in this, so the question is D the correct value at setup time? So here's the setup time, is at 2 nanoseconds before the clock edge. So it looks like D is the correct value because we were expecting 1 and it was 1. So okay, so is there a setup time violation? There's not a setup time violation because at the setup time, the value is correct. Okay, so then we keep going. Okay, let's see if it was held for long enough. Was it held? Oh, actually, it looks like it changed. It changed before the hold time expired. So therefore, what violation is this? This is a hold time violation. Yeah, which is maybe a bit confusing because maybe you looked at this and you were like, oh, well, but it changes the value before this clock edge. So it looks like it would probably be setup time, but no, setup time is just this instantaneous moment right here. It's like, was it set up exactly like right before the setup time? And in this case, it was, but it just wasn't held for long enough. So this would fail hold time. Okay. Cool. Yeah, I think about 50% of the class got this correct. So maybe just double check. Okay, everyone look up here. So everyone agrees now that this is a hold time violation, right? Any confusions on this? Okay. Okay. Probably the people who are confused are the people who are not here today. So please, if you know anyone who's not here today, go and make fun of them that they got this question wrong. Because it's like, oh, like if you went to lecture, you would have got this question right. So, okay, cool. So this was a hold violation. Okay, now let's just quickly do this. So assume 3 nanosecond setup time. So what region on this timeline would be the timing aperture for part C? So starts at 2 nanoseconds and goes until when? Yeah, cool. Okay, so it's just this region right here. And is D held at 1 for the entire duration of this? Yes. Yeah, so therefore, what is the violation? No violation. Cool. Okay, good stuff. Now I want to remember, what was the other question? Cool. And yeah, so the last question that I wanted to go over right now was this one. So for the most part, people did very well on this, but let's just walk through it again. So this question is asking what is the maximum clock frequency at which this multi-operand adder can operate. So what things do we need to add up in order to figure out what the minimum clock period should be for this? Setup time. What else? Clock to queue. What else? Combinational delay. Okay, what is the combinational delay? Yeah, it looks like it's just whatever the delay of the 16-bit adder is, right? We don't need to worry about the buffer because we're saying that the buffer is not included in this schematic. So, okay, cool. So we just add these things up. Why do we not add the hold time? Anyone? Yeah.
Because that's like during the clock to queue, like time, or it's.
Right. So yeah, if we go back to like this diagram, hold time doesn't necessarily mean like how early D needs to arrive. It's just basically just how long is the signal going to be held for. And the signal is going to be held for at least the combinational delay. But it doesn't actually denote like how fast we need to change our clock frequency. Like right here, this clock, we don't know anything about its frequency, but no matter how fast we make our clock, there's never going to be a case where we need to like add our hold time to determine like what our maximum clock frequency is, because we can make this clock basically go as fast as possible, and our combinational delay or our clock to Q delay will be the thing that is like much greater than it will never get to the case where our clock is affected by our hold time. So okay, cool. So these are the only things that we need to add up. So let's quickly add them. So that looks like it's 5, so 17 nanoseconds. Okay, so if we have a 17 nanosecond clock period, then how do we convert this into frequency? So it's going to be 1 over that. To turn that into, so let me quickly. So 1 divided by 17 would be 0.058. What units would I put here? So if we convert from nanoseconds into a frequency, then what would that be? This would be gigahertz. But this is really gross to have this format. If I came up to you and was like, oh yeah, like we're operating at 0.058 gigahertz, you'd be like, what? Like this doesn't make any sense. Instead, you would want to put it in megahertz. Okay, so how do we convert this into megahertz? Multiply by 1,000, yeah. So then this would end up being, so we would probably just say 58 megahertz. Okay, yeah, a lot of confusion on just this act of converting between units. So go and make sure you practice this, make sure you understand this, okay? And now this question is saying we'll redesign to now handle 6 inputs instead of 8 inputs. I noticed that a lot of people thought it said 16 inputs. About maybe a fifth of the class had it work with 16 inputs instead. So I gave you a little bit of partial credit because like so many people misread that. But yeah, so only 6 inputs. So if we have, so probably a very similar style, but we're going to have 1, 2, 3, 4, 5, 6 inputs. Okay, what should our first kind of pipeline stage probably look like? So remember, so that it looks like this up here for 8 inputs. So how do we modify this to now be 6 inputs? Yeah.
Is it only 3 adders instead of 4?
Sure, okay, so we could use 3 adders for this section right here. So maybe an adder right here, adder right here. There's a few different ways we can do it, but absolutely, that works. Okay, and then what do we do for the next stage? So we have 3 inputs. So what should we do? Yeah.
An adder and a buffer.
Okay, sure. So if we do an adder, we can add in these 2, but we probably don't need like another adder right here. We could like add 0 or something, and that would be fine because that would now add additional delay. But probably, yeah, you could just add a single buffer. Also, okay, what's the symbol for a buffer? I noticed a lot of people were getting this wrong. What is the symbol for a buffer? So a buffer you can draw as 2 inverters. So if I draw this symbol right here, then what will the delay be? So this right here is 3 nanoseconds because this is 1 buffer. What is the delay of an inverter then? 1.5. Okay, cool. So you can draw out a buffer using this symbol. You can also, if you want, just not put the little dot right there, or not put the little circle. The circle is the thing that denotes that there is an inversion happening. So you could also just put it like a triangle right here. This is also a reasonable symbol for a buffer. So both of these symbols are the exact same, and both of them are 3 nanoseconds, and they're both just 2 inverters, put one right after another. Okay, so this is the inverter. This is the buffer. So sure, we can put that there. Good. So now after that, then we just have 2 inputs, and so it's really easy. We just take another adder, and then we're done. Okay. Yeah, any questions on this? Is this what we were expecting? Cool. Okay, good. So the final is going to be cumulative. So you will have a chance to redeem yourself on any one of these questions if maybe they didn't go quite as you were planning. Definitely make sure that you understand why this question was a hold time violation. A lot of people were misunderstanding that. And also on the final will then cover some behavioral Verilog and state machines, and then also a bit of serial communication, which we will talk about today. And then also some more advanced optimization techniques that synthesis tools will take advantage of. We'll learn the more advanced optimization techniques later. Okay, cool. So I want to go back to an example that we did on Monday. So on Monday, we were tasked with this problem where we wanted to make a more space-efficient multiplier. Because remember, the multiplier that we had made before used like a ton of flip-flops, used a ton of adders. It was very fast, right? It passed the data through basically like a hierarchy, like a tree of adders, and produced the multiplication output very quickly. Maybe we didn't actually need it to be that fast. Maybe we're okay with having it run just a little bit slower, but also like we really need it to be more space efficient. And so we came up with this sort of interface where we have A, B, and then load. And so load will load in A and B, and then after some number of cycles, it will then produce the output Y, and it will also produce a signal saying, hey, I am now valid, you are able to read me, and I will be the correct product of A and B. And and the way that we did that is we took, this top number represents A, this bottom number represents B. What we did is we noticed that you can shift along this top number by 1, and then every time that you shift it over, you can just also shift over this bottom number to see whether or not we should actually add that. So here we can see that starting out in position 0, we should not add this number. Then we go and we shift this, and then we can see that we're also not adding this number. And then we shift it over one more time, and we see that we do add this number. Shift it over one more time, do add this number. And at the same time that we're shifting this bottom number, we're also shifting this top number over by 1. This is just kind of standard multiplication algorithm, but just explained a little bit more verbosely. And then we were able to come up with this diagram. And so with this diagram, you can see the top number is being shifted to the left, bottom number being shifted to the right, and we're checking this least significant bit here, and this is what determines whether or not we are adding this top shifted number. And so this design right here is all we kind of needed in order to implement this adder, this multiplier unit. And we also noticed that we could produce a valid signal if we just check this output right here, and if this output is equal to 0, then that means that we are currently, we finished everything, and so now we are outputting the valid output. So, but if we wanted to have a little bit more flexibility over this, maybe we wanted to have an option where we can pause it midway or just other things. It would be actually very helpful to have a state machine. if we have a state machine that's kind of orchestrating this design, then it just gives us a lot more flexibility and the extra kind of features and things that we can add. You'll see that this will be very helpful. So if you remember, so this was the state machine the kind of naive state machine that we started with. So the idea is that we have an idle state and a working state. And when we are in idle, that is when valid equals 1. And then when we receive a load signal, then now we enter working. And working will run and run and run and run until finally now xbq, so which is right here, xbq now equals 0. And once that equals 0, then yeah, we return back to valid. So yeah, so with this state machine, we are able to kind of characterize what is happening inside this. But now the next step is adding some additional signals to our interface. Okay, so I have this signal right here that I kind of crossed out. It's called valid. And valid is probably going to be pretty similar to load. So let's now kind of replace load with valid. In your opinion, what would the difference between valid and load be? Specifically valid in, like you can see it's pointing in. Yeah, what does this mean, valid? How does that compare to load? Yeah.
Does that say like whether or not the number is ready or like?
So yeah, exactly. So it denotes whether A and B are currently valid. Yeah, or maybe like the thing that was sending out the data is, I guess, ready to send that data out. Okay, yes, but what is, so valid, all valid says is just like that A and B are valid, but load says like, okay, like please load in these values. What is kind of the difference between load and valid? Yeah.
It's load, kind of like you're just throwing in a value, it's just getting in, or like valid is checking to see if it's like an 8-bit value.
Sure. So it's close. So if we look back at this, so yeah, notice that when load goes high, no matter what, it will just always it'll be inserted into this circuit. So when we receive a load signal, even if we're in the middle of an operation, then now the data will get kind of overwritten. And this is not very safe, because if maybe you decided, like, yeah, halfway through an operation that you wanted to like start loading up a new operation, then whatever you were previously trying to compute would be all corrupt and nothing would work and you'd all be sad. So instead of load, you could instead put a little bit more responsibility into this circuit. And so instead of just load, maybe you could say like, hey, the input is currently valid. However, you don't actually need to like load it right now. Instead, maybe you could wait until you are ready to receive this input. So that is the whole purpose of the ready valid interface that I'm sure you've looked at lab 5 and maybe you've started that. So lab 5 is all about the ready valid interface. And the whole idea with the ready valid is that it won't like overwrite anything that's happening inside your circuit. It's a very kind of safe way of sending data from one chip or one circuit inside of a chip to another circuit inside of a chip. So okay, so instead of load here, just like completely just overriding whatever we have, how could we instead modify this to now take in a value correctly given a valid signal? So when the data is valid, how do we know we should actually load in that data? What do we do? So if the data is currently valid, how do we know when we should actually load it? Yeah.
Should we add another mux and like have one of the inputs be load and one of the inputs be like 0 and then the select arm is valid?
Ooh, I think that would not actually do anything, because I think that would basically just be the exact same thing as just plugging in valid as load. I guess what I'm thinking is we actually just get rid of load altogether. So we're basically replacing load with valid. But yes, I do agree. We should probably maybe have some sort of extra logic, maybe a mux, maybe a gate or something. Yeah, any other ideas? Yeah?
Would you just check the state that you're in?
Sure, okay. So when should we actually take in this valid input? What state should we be in?
Idle.
Okay, great. Yeah, so if we're in idle, probably means that we are not running anything. And it's probably fine if we now read in this valid input and then we can now load it. So instead of load, maybe we can replace this with, so I'm gonna delete this. So instead of load, maybe I could say, so both valid in, and I'll just say idle. Okay. And so now this is much safer. We're not going to accidentally like overwrite any data, and now our whatever is on the output won't see like garbage and then more garbage. Okay. Cool. Valid in. But okay, well, so maybe now the thing that sent this data over to us, maybe it sends valid for a couple signals, but now it doesn't actually know whether this multiplier actually received that data. Like if I'm broadcasting like, hey, like I'm sending out a bunch of data and this data is all valid. Okay, it's valid. Hopefully someone can use it. Okay, how can I know that this chip is actually taking in the data that I'm broadcasting? What is the other signal that you were using in your lab? You can shout it out. Ready, yeah. So this circuit should probably also output a ready signal. And if you have the case where this circuit is both receiving a valid signal and it is also at the same time sending out a ready signal, meaning like this circuit is broadcasting that it's ready, and a transmitter is sending in valid data. If there's both a ready input and a valid input at the same time, then that like is a guarantee. That is it's like a handshake that there must be data flow at that time. And so if now it sees, if idle and, if ready and valid are high at the same time, that is actually probably the real reason, that is the real way to ensure that, to determine when load should be activated. So instead of idle, I'm actually going to replace this with ready, and then we will implement a ready signal. And so will ready be an input or an output here? Try the other one.
Output.
Yeah, so this will be an output. You can think of, because this circuit is broadcasting that it's ready, and it is also receiving whether or not the input is valid. Okay, there we go. But now we need to determine when we are ready. So when are we ready? Yeah.
When we're in the idle state?
Exactly, yeah. When we're in idle, that's when we're ready to receive more data. Perfect. Okay. So, well, yeah.
Being valid and ready then.
So, yeah, great question. We'll talk about that interface in just a second. Yeah, so I'm going to make this a little bit clearer, and I'm going to make sure. So this valid right here, this is valid out, because this valid is whether or not the product is valid. But yeah, let's also probably copy this down, at least for now. and drive ready out. And this is the that you can think of this as the input is ready, and this is the output is valid. Okay, good. So that's ready out determined. But if we're also sending a valid out signal, then what is the final signal that we are probably missing here? Yeah.
Valid underscore I.
So we have valid underscore I given as an input. What's the other one? So it is going to be an input. Yeah, ready input. So the ready input will be paired with this valid out, and that is determining whether the receiver of this data is actually ready to receive this data. And if there is if like the receiver is not able to receive the data, then that means that this circuit must now stall. It must stall until it's actually able to send out that data. Like if something's not ready for you to send out data, then you need to wait until that thing is ready. And then when it's ready, then that's when data flow occurs. Okay, good. So let's kind of take inventory of everything. So we have on our input, what was like on our input port, like when we're taking in like the values A and B, what was the ready valid interface? What was the input and what was the output? Yeah, so we will have valid input. And the valid input just, specifies whether A and B are valid. But then at the same time, we need to broadcast whether we are ready to receive that input. And then similarly, so on our output port, we will result in the product. And then we have a valid, is this a valid input or valid output? This is a valid output because we are telling our receiver that our product is going to be valid. And then we also have a ready input. And this determines whether our receiver is actually ready to receive this product. And if we have the case where we are valid on our output, so let's say at this point we now have a valid output. Well, if we are not ready for a long time, then in this period kind of right here, we need to make sure that we stall, and we also need to make sure that probably we don't accept any more user input. So any case that we are both maybe valid and also the ready input is not ready, then in that case, then our ready output up here should probably also be 0. So let me draw that out. So let's say right. I'm going to slide this over. Okay. And let's start from the beginning actually. So let's say initially, so we receive a valid input. Maybe starting out from the beginning, we were always ready to receive that. So then now we just received something. We have the case where data flow happens right here. Okay. So data flow happened. And then now, in this initial state, kind of right here, right before the data goes valid, what do we probably imagine that this region is? So if we received valid input, and also we were ready, but then ready now goes back down. We're no longer receiving valid input. But then we wait for a bit, and then finally we send the valid output. So in this period, what is probably happening here? Yeah? Yeah, so this is the multiplication part. This is the calculation. So in this region right here, our circuit is working. So maybe this is like the working state. So yeah, I'll call this in calculation. Okay, and then right here, we stall. Stall until ready, because currently ready is low, and then maybe finally now ready goes high. And so once ready goes high, then finally now we have both of these are high at the same time. So then data flow occurs and everyone's happy again. This probably goes low again, or maybe that stays high. This probably goes low. All right, does this kind of make sense? So this is basically what your lab is. So the ready valid interface is extremely popular. This is basically the number one way that you get data from one part of your chip to another part of your chip. It's extremely fast. It doesn't take many wires. It's just whatever, ready valid, and then probably a ready valid input and a ready valid output. And then you also have your ports here. And if you've heard of parallel communication or like a parallel interface. So this is a parallel interface because we are sending the entire width of A and the entire width of B all in one go. This would be separate from like from a serial communication where maybe you sent each individual bit of A and B like one after another. So if you are familiar with USB or SPI or I2C, or like there's a lot of different serial communication protocols that involve like sending one bit after another after another. In this case, we send the entire signal just all in one go. And and so in this case, first we receive the data in, then we do some sort of state machine thing, and then we stall probably inside of our state machine, and then finally, when we receive ready, then now everything kind of resets back to the beginning. Okay, so that is the ready valid interface. Okay, so this project right here, this was made by the University of Washington, their bespoke silicon group. This is base jump STL. If you take CSE125, then I'm certain that you will see more of this. This is one of the most popular open source collection of Verilog IP. So if you pull up any one of these files, so they have like a floating point unit that you can use. They have all sorts of serial communication stuff. They have like memories that you can use, FIFOs, like all sorts of really, really great stuff. I wanted to also just show you this. So this is their multiplier that they have, their iterative multiplier. That's what this I stands for. Iterative, meaning it's basically the exact same algorithm that we have implemented on paper. And inside this, and this is a module that is used by thousands of designs. Like one of the most famous iterative multiplier implementations in Verilog. And we can see right here that we have, well, it's not as nicely named, but this VI, do we know what VI stands for? Oh, incredible. And then we have ready and, you could ignore the and, it's just ready. So here's valid, ready, valid, okay. And then here we have the inputs, okay, so operation, this determines whether it's signed, I guess. Then here we have VO, what does this probably mean? Valid output, and then UMI, I don't know why they call it this, but this is ready input. Cool, so there we go. So one of the most famous yeah, implementations of the of a multiplier, and we could look through like basically any one of these files. If I open this random one, I've never opened this, and I guess it has a valid, but I guess it doesn't have ready. But for the most part, most of these functions most of these modules have a ready valid input anytime there's a state machine inside of it, because ready valid is the most kind of common way to initiate and stop and progress state machines. So that is kind of the whole purpose of talking about ready valid is like, yeah, anytime you ever have a state machine, which is basically just all the time, like you just always have chips with state machine, like you can have thousands of state machines, you're probably going to have ready valid interfaces that connect to it. Yeah, and you will learn way more about ready valid in CSE 125, the advanced Verilog course. So highly recommend taking that. I think it's offered in fall usually. So yeah, you can take it next year. Cool. Okay. Yeah. Great. I use this repo all the time. If you are ever interested in looking up a really high quality example Verilog, yeah, highly recommend looking through the base jump STL. Lots of really good stuff in here. Okay. Yeah. Question. CSE 125. Yeah. Cool. Good stuff. Okay. Oh, you know what? Okay. No, this is good. We're going to do a quick participation quiz. That's what we'll do. Okay. So these are the questions. I'll open the box in just a second. So the first question is, when does data flow occur in a ready valid interface? The second question is, write all of the ready valid ports for these three modules. Ports meaning like Verilog ports, so you should list all of the inputs and outputs for each one of these three modules. Okay, begin. Okay, cool. So let's talk about it. So when does data flow occur in a ready valid interface?
It's ready valid.
When ready and valid are
True.
both high. Yeah. Okay. So when ready and valid are both high. By the way, this is probably question 1 in a technical interview for Verilog. It's like, oh, like, hey, ready valid interface, when is ready valid, when does data flow occur? And you say, when ready and valid are high. Yeah, cool, okay. Cement that into your brain. That's like basic question 1. Basic question 2 would be like, how do you create a flip-flop or something? And you would say, always FF. Okay, cool. Okay, good. Okay, so now imagine this diagram. So let's write out A's ports. So what does A have?
Ready out. Valid out.
Valid out. Okay, valid out. What else?
Valid
And ready in. And that's it. That denotes this section right here, right? There's no valid in that I've denoted. Like, we could imagine that maybe there's an arrow pointing in here, but I didn't draw it, okay? So we just have valid out and we have ready in. So B is saying like, hey, I'm ready to receive this. Okay, cool. So that is A. Now what is B? So first, let's do this port. So first, what happens is we have valid in, and then what is the ready signal? Ready out. So B is plugging this probably into A. Okay, and then after that, then what do we have? Maybe valid out. Yeah, ready in. Okay, and then C. So let's keep. Let me make it so that anything that is on the same vertical line is being plugged into each other. So I'm going to move this along. So over here, we're probably going to have a valid input that the B's valid out will plug into. So B will plug into C, its valid input, and it will also plug in this ready output. And so every time that you have like two nets that overlap vertically, then that denotes that that they are connected with each other. Yeah, question.
So is like valid kind of just like the previous letter, if that makes any sense? Like why
Right, so we definitely do as well. So valid and ready, this just denotes whether the inputs are good. So yeah, so we would probably, like paired along with this is we would be sending in like, yeah, whatever, product underscore I at the same time. And we'd be feeding in sum underscore I. And so every time we have a ready valid interface, which takes, yeah, I guess kind of these 4 wires all connected. Technically, it's only 2 wires. But yeah, if we have these 2 wires now, there's also just going to be data that is paired with that. And these wires denote whether the data transmission actually occurs. Cool, there we go, okay. Good. So this is solution. So this is the most common on-chip this is the most common on-chip communication interface. If maybe you wanted something that was, let me restate that. So remember, so this is a parallel interface because yes, we're sending like just like single bits here, but we will at the same time we could be sending like a 128-bit value, and we could send this value, and it happens at the exact same time that both ready and valid are true. So we maybe have a 128-bit bus that is paired with this ready valid interface, and so this is considered a parallel port because we are sending all of the data all at the same time, and that is totally reasonable on a chip because your wires and everything can get really, really small. So it's okay to just have like 128-bit buses that are just super wide. It's fairly easy to route them because on a PCB, right, printed circuit board, has anyone made a printed circuit board before? Design one? Okay, that's actually way lower than I was expecting. Okay, is that required for any like courses that you've had to take, or you just like did it? Yeah. All right, well, printed circuit board. So you are able to design your own circuit board. And usually you're probably limited to about 4 metal layers. You can get PCBs that have like 20 layers of metal in them, but for the most part, maybe you only have like 4 layers. So if you want to route like wires throughout your printed circuit board, it will like kind of go up through vias and snake around, but you only have like 4 possible hierarchies that it can be at. You can't have it be like, it can't go continuously throughout the entire board. There's only 4 possible like levels it can be at. Versus in chips, you will like definitely have at least 20 layers of wires. Like you can have incredible like routing capabilities through your chip. There's just so much room for your wires to route around, and so it's kind of okay to have parallel ports inside of your chip. But the second that maybe you want to go outside your chip, then now you don't really want to do any parallel ports because the actual like wires that come out of your chip or like the pins, like if any of you have used like integrated circuits before, maybe you've used like little like TTL chips that you've plugged into breadboards. Usually those only have maybe like 20 pins total, like little chips. And people know what I'm talking about? Getting a lot of vague looks. Okay, cool, yeah. So if you have a chip, right, it only has maybe like 20 pins. But inside of a chip, you can have like thousands or millions of wires inside that. And so there's actually this concept called Rent's rule. And basically Rent's law or something. Basically the idea is that you want to design circuits that have very few output pins, like that come out of your package. And instead you want to maximize the number, you want to maximize the ratio of wires inside your chip to wires outside your chip. Like you don't ever want to have it be like that if you make your chip like twice as large, that you also at the same time are making the number of output pins on your package, like doubling the number of package pins. Because if you start with like 48 pins, and then the next time you release the chip, now there's 196 pins or something, then you've now had to increase your cost a lot because now the actual like package is a lot larger. Anyways, so this is just a big rant saying that instead of doing parallel ports when doing like chip communication, Instead, we use serial communication. The whole purpose of serial communication is that maybe you only use a couple wires for an entire interface. Like here, we are using a bunch of wires. So we could potentially be using like 130 wires if we were transmitting like 128-bit data. So, so instead of doing a parallel port on a chip, you could probably use a serial interface. And one of the most common serial interfaces is called UART. Have people heard of UART before? Okay, cool. Where did you hear about UART? Yeah.
ECD 13.
13? Okay. What did you do with UART?
We did communication between two PIC32s.
Cool, sure. Yeah, great. So that is, a great use of UART because you can't plug in a bunch of wires like across the chip. Like it's much better to only have just a couple wires. Right, and like basically any sort of communication interface that you can think of is probably going to be serial. Like HDMI, USB, Ethernet, like basically anything that you can think of. PCIe. These are all serial communication interfaces. And so the idea with UART. So I want to quickly just go through this really quick because there's going to be some homework questions on UART. So I just want to kind of get this out. UART is fairly straightforward to understand. There's a lot of great resources online so if you're looking for more help on this. So the idea with UART is that if you want to do like chip-chip communication, you will have a transmit pin and a receive pin. And all this is just a single bit, but this will oscillate. And this, depending on its oscillations, you will send like one bit of it at a time of your data that you're sending. So the transmit pin will then be plugged into the receive pin, transmit pin plugged into the receive pin. They do this twisting pattern if you're doing chip-chip communication. You can also, if you only wanted to just send data out, then you could just have one wire. But if you wanted to also have data sent back, then it would be two wires. Okay. So this is the general idea of UART. So by default, we have this idle state. So idle, so it's held at probably 3.3 volts, or if you're doing it on chip, for some reason you are on chip, maybe you keep it at 1 volt. And then you receive a start bit. So the transmit pin will then send like a 0 volt pulse. And then after that, then it starts sending each of its data bits. And so in this case, so it looks like, it's sending whatever, 1100 so whatever this number is in binary, maybe this is an ASCII character or something. So it sends all of this data. And then it ends the data with one extra final bit. This is not related to data, but instead this is the parity bit. Have people heard of parity bits? Does anyone know what this is? Okay, can I get an explanation of what a parity bit does? Someone? Yeah?
So in this case, it's going to there's even or odd ones.
Exactly, yeah. So the parity bit is a way to check if an error occurred. It's not super, it doesn't work 100% of the time, but it's pretty good. What it does is it will send you can configure it either way, but in this case, it will give a 0 if there are an even number of ones that were sent in the data. So what happens is maybe you have a single bit that is misread, or a single bit is flipped. But then maybe your parity bit still says 0. And then you can, as you transmit it, then you can double check. You can see okay, so if I received the parity bit as 0, but I received an odd number of ones, then that clearly means that there was an error in the data. And so what I can do is I can send back some sort of message that's like, hey, there was a mistake, please can you retransmit out that data? And then most likely it will just resend the data one more time. Yeah, question?
How does it know that bit is a parity bit and that's not just going to continue the signal?
Oh, right. Great question. So in UART, you will also determine ahead of time, you will determine the number of bits, the number of data bits in each transmission. So in this case, what is this? 1, 2, 3, 4, 5, 6, 7. Yeah, so it looks like there are 7 data bits being sent out here with 1 parity bit. Probably you will most likely only use 8 data bits. If you're sending ASCII ASCII is only 7 bits, so maybe that's why you would want to use 7 bits here. You can also, if you wanted, you could extend it out a little bit further, but generally it's generally locked to 8 bits. Yeah, so this is UART. You may also notice that there is no clock signal that's paired, right? If we look at this diagram, right, it's just transmit and receive. There's no clock signal. But like very clearly, if we're sampling this, like if we're polling this, if we are the receiver and we're looking at this, then, well, how do we know that, how do we know like exactly like when each time should line up? Like what if we're looking at this and maybe we sample here, I don't know, sample like in the middle of that. So how do we make sure that our clocks are synchronized? Does anyone know? Remember? Yeah. Okay, yeah, what do we do? Yeah.
You have a preset bit there, and then let's get what place that.
Exactly. Yeah, perfect. So what you will do is ahead of time, you will like predetermine what clock rate like you agree on. So both your transmitter and your receiver will be intentionally running at a very specific clock frequency, and this is called the baud rate. So the baud rate is usually pre-specified, and if you've ever used like Arduinos or things, if you're ever using like serial print line or whatever it is, then in that case you will need to specify the baud rate in order to make sure that your computer can communicate with the Arduino over UART. Cool, so let me just scroll through this one more time. Yeah, cool. So this is UART, a very common communication interface. I thought it would be probably useful to just kind of throw in some serial communication ideas at you, because you will undoubtedly see them hundreds more times throughout your careers and potentially here at Santa Cruz. So I just wanted to throw them in while you're in the headspace of thinking about bits and waveforms. And then I guess just the super last final thing. So right here, this is the Alex Frencich UART implementation. Alex Frencich is like a world-renowned, internationally renowned Verilog engineer, and he has a really fantastic UART implementation. And yeah, so if you were ever interested, you could look through this code. One thing that he does though is he doesn't separate out his D and Q values in his always pause edge clocks. So don't learn from him in terms of that. It's an old style. The base jump does use D and Q, but anyway, so I'll probably link this as well. This is a great implementation. Oh wait, and then final thing, what does that say? Valid ready. Okay, so this implementation does use ready valid, and then it sends out its data over UART. Okay, yeah, thank you everyone. I will see you on Monday.